Welcome to Certainty, where we make assurance double sure. In this video, we are going to look at the deflection of beams. Deflection, in structural engineering terms, refers to the movement of a beam or node from its original position due to the forces and loads being applied to the member. It is also known as displacement and can occur from externally applied loads or from the weight of the structure itself. Deflection can occur in beams, trusses, frames, and basically any other structure. Let's look at a simply supported beam. This is what the beam looks like before any load is applied. If we apply a concentrated load at the center, the beam will bend. Vx is the displacement, which is known as the deflection. This can happen to various types of beams such as cantilevers, continuous beams, fixed beams, and overhanging beams. This can happen due to various types of loads such as point load, uniformly distributed load, and uniformly varying loads. There are several methods for finding the deflection of beams, including double integration. This method involves integrating the equation of the elastic curve twice. The first integration yields the slope, and the second integration gives the deflection. Then we have the moment area method. This method uses the area of the bending moment diagrams to determine the slope and deflections at specific points along the beam. Thirdly, we have the conjugate beam method. This method is used to find the rotation and displacements in beams. Lastly, we have the superposition method. This method is used to determine the deflection at a point when there are multiple loads acting on the beam. In this tutorial, we are going to look at the double integration method. The formula for the double integral method is given by EI times the second derivative of I with respect to x equals plus or minus m. We put plus if the bend is convex. E is the Young modulus, which is a property of the material that tells us how easily it can stretch and deform, and is defined as the ratio of tensile stress to tensile strain. I is the moment of inertia and m is the bending moment. Now let's look at an example. A simply supported beam shown in the diagram has a circular cross-section of diameter of 100 millimeters. A load of 3 kilonewtons is applied at its mid-span. The material from which the beam is made is steel, for which E equals 210 giganewtons per square meter. Determine the deflection at a point 3m from support A. Support A is a pin and B is a roller. The length is 4.2 meters and the force is acting at the center. We are told that the cross-sectional view is circular. We are also given E, and here is our question. Let's write our formula. We are putting negative since the bending is concave. This is what is going to happen when the load is applied. You can see that the center of the beam is the critical point, so we are going to make a section at the center. Now we have two sections and our point of interest lies in the second section. Since it's a simply supported beam, we are only going to have upward reactions at points A and B, which means we can write our equilibrium equations if we resolve upwards. We are going to have FERA-RB equals 0 and we name it equation 1. Remember F equals 3 kilonewtons. Of course, we can't find RA and RB with one equation, so we need a second equation. I'm going to take moments about point A. The counterclockwise direction is my positive direction, and the sum of moments about this point should be 0 since the beam is static. RA passes through the point, so the moment is 0, and for FA is force times distance, which is 2.1 meters, but is acting in the clockwise direction, that's why it's negative. For RB is force times distance again, and the distance is 4.2 meters and the direction is positive. Now let's simplify, and RB will be 1.5 kilonewtons. We can find RA by substituting RB in equation 1, which gives us 1.5 kilonewtons. Now to find m on the double integration formula, we cut the beam at point x meters from the support A and make sure that the point is after the load. Let's call this endpoint E. We want to take moments about this point, and Vx is the downward deflection. The counterclockwise direction is my positive direction, and the sum of moments about this point should be 0 since the beam is static. The distance between E and F can be obtained by subtracting 2.1 from x. F is going to produce a positive moment and RA a negative moment, and remember to multiply the force by the distance between the 2 points. For F is x 2.1 and for RA is x meters. Let's make m the subject of the formula. We have MEI. It's now time to find the moment of inertia for the circular cross-section. The moment of inertia is given by pi d to the power 4 over 64. Let's change millimeters to meters by multiplying 100 by 10 to power -3. Now let's plug in the values, and I will be pi over m to the power 4 over 640,000. If you haven't subscribed to our channel, please click the subscribe button and turn on the notification bell so that you won't miss any upcoming videos. Now let's substitute m into our formula. To remove dy dx, we integrate both sides twice with respect to x. If we integrate the second derivative, we get the first derivative, and on the right-hand side, if integrate x, we get x squared over 2, and for x minus 2.1. We are going to use chain rule because if we don't use the chain rule, our answer will be incorrect. That's the limitation of the double integration method. Since we are integrating, we're going to have a constant of integration. Let's call it C1. Now we are going to integrate again. On the left-hand side, we are going to be left with Vx. You can call it y. Remember, EI is a constant, that's why we have been ignoring it all along. On the right-hand side, never expand the brackets. So we are going to add 1 to the powers and divide by new powers. Since C1 is a constant, if we integrate, we x cone. But we have to add a constant of integration. This time, let's call it C2. You can choose any letter. It is a matter of self-preference. Now we have two constants with unknown values. We use boundary conditions to find the values of constants. If we draw the deflection curve, you can that at the center point, the gradient will be 0, which is the angle rotation. The center is half the length of the beam, so we can write our boundary condition. If we go to point B, since we have a roller, there will be no deflection because the beam can easily tilt. So let's write the second boundary condition. Now let's sub equation 1 into equation 3. Remember, x is our point of interest, which is 3 meters. L is the length of the beam, which is 4.2 meters, and dy dx is 0. To find the cone, we just need to make C1 the subject of the formula and simplify. C1 is equals 3.75 kilonewtons per square meter. Now let's sub the second boundary condition into equation 4, and Vx equals 0. C1 is 3.75 kilonewtons. If we simplify, we get C2 as 0. Now we can write the deflection curve equation. Remember, EI is a constant, which means we can divide both sides by EI to make V subject of the formula. We have a IIx. But as you can see, E is in giganewtons. Let's change giganewtons to newtons by multiplying by 10 to the power 9. We are also going to change kilonewtons to newtons by multiplying by 1000. Now let's simplify, and if we do that, we get Vx as 0.34 meters.